Welcome. In this session, we'll review decision-making using regression, another one of the most popular techniques for managers or any business to help make decisions. In this session, we'll be looking at how we can use regression to actually help predict the future. In fact, this is the first technique that actually produces a model that allows us to anticipate or evaluate the possibility of values that are outside of our actual sample that may be present in the population. We'll explore how we can use this with more than one predictor and with a single predictor and compare their usefulness for us to make decisions. We'll also be looking at a different method to help us predict the likelihood of different events. To expect the unexpected shows a thoroughly modern intellect, an homage to Oscar Wilde because, well, why should the Smiths have all the fun? Simple linear regression. This is really where managers are seeking to make decisions based on some kind of relationship between two or more variables. When we're evaluating something and we get a model for it, which is going to be very clear in just a moment, we can actually do additional things than only understand the sample that we have our data on. We can actually extrapolate on that sample and use this model to evaluate other values. So in a way, it's actually looking into the future to try to understand what may happen. We'll be doing that by looking at a single dependent variable, but that dependent variable will be predicted by a number of independent variables. Some writing describe independent variables as predictor variables and also use the word response variables for a dependent variable, but it's all the same thing. Simple linear regression is going to be using one of those independent variables as a predictor and one dependent variable. The relationship between those two variables is going to be described by a straight line. That's why it's called linear regression. There are other techniques that we can use to evaluate different types of data or relationships besides linear regression, but that's the most popular. And if we use more than one independent variable, we'll call that multiple regression, and we'll be demonstrating both of those in this session. So the equation that describes how something that we're interested in, the dependent variable, is related to independent variables, which is what we'll be noting as x, and an error term, that will be our regression model. It takes a really familiar form if you know the form of a line where we have some kind of an intercept of this regression line. I'll describe this in just a moment. This is going to be our slope of the line, so the run and rise of the line. And then x is going to be some kind of independent variable, predictor variable that we're going to be plugging in. And by plugging that number in, once the line is estimated, we'll be able to actually predict an outcome on the dependent measure. The intercept is basically where this line connects with the dependent variable. For example, on the plot, it's going to be on the y-axis. And what's important to understand about the intercept is that if there's absolutely no relationship in whatever predictor variable we have, this value, b1, which is representing the value of the predictor variable, would be 0. And if this is 0, any value that we were to select for our predictor variable would also be 0. And therefore, the intercept, if there's no relationship, it's really just the mean of whatever the dependent measure is, because that's the best predictor that we can have for a variable's value if we know nothing else. And so if there's absolutely no relationship, then it's really no better than just predicting the mean. If there is a relationship, you can see if this value is non-zero, and then even some non-zero integer for either of these, it's going to adjust the y-intercept. And so I'll demonstrate that for just a moment. But that'll only be the case, of course, if there is some kind of relationship to help us predict it. The values for the actual predictor variable, which is the slope, it's a little bit more involved, but actually if you examine these notations, it's really pretty familiar at this point. We're just looking at our independent variable for all its observations, the y variable, or the dependent variable for all its observations, and then we'll be calculating some means. So it looks maybe worse than it actually is, and I'm going to illustrate for you conceptually what this is in just a moment. When it is actually finished, what we're going to see is a regression line, which this is going to be our independent or predictor variable if you were to plot it on the x-axis, and the dependent variable on the y-axis. The regression line will take this sort of a shape if there is a relationship between the two variables. In this case, we're looking at a positive relationship. This also should seem somewhat familiar, as it is very much related to correlation. In fact, there's a direct relationship between a lot of these measures and correlation. If we had more time, we could explain that, but we can look at that in maybe a future session. If there, you could also take the shape of a negative relationship where we'd have a negative slope. So as the values on the independent variable are increasing, we're seeing the values on the dependent or predicted variable decreasing. So it could be a negative value, and that would be indicated on this slope. Or there could be no relationship at all. If there's no relationship at all, as I was sharing earlier, it's really no different than just predicting the mean for whatever the dependent measure is. And that's the value where the intercept would be. If you put that all together in simple linear regression, I've given an example here that you could study how all of these numbers get plugged in. Again, I think that it looks more intimidating than it actually is, but you'd be able to see how the values of the intercept and the slope come together. What's important is to look at how the final form takes shape. This is our intercept. This is B0. This is our B1, which is the value that we have estimated for our predictor. So there is a slope. And now any value that I select for my independent or predictor measure could be put in here. And we would be able, in this case, to look at how the relationship of web ads viewed relate to eventual site visits. That's what the model is that we just predict. And the interpretation of that would be for every unit change in the independent variable x, y will be changed by some amount. You can see that here just intuitively. If this value goes up by 1, the predicted value for the dependent measure is also going to be increased. In this case, for every web ad viewed, the website visit increases by 15. Because if this were one additional web ad viewed, we would be able to see that the y predicted value of website visits would go up by the value of 15, just the adding of these two together. This is actually super powerful. We're predicting values in a population even though we have not actually perhaps seen those values in our sample. Because you could plug in just about anything here. Maybe they actually viewed 10 ads. You can see we didn't actually have 10 ads in our actual sample. This was the values that we actually had in our sample, but the model is now predicting if they did view 10 ads, what the likelihood or what would be predicted for them to actually visit the site. So that's the power of regression working there. This is how it would actually look if you asked for a scatter plot to be fit with a line. Again, this should look somewhat familiar to regression. Regression looks somewhat familiar to correlation, excuse me. And here we have on the x-axis the predictor variable of web ads viewed, and as web ads viewed increases, we see the visits to the website are also increasing. In fact, if I were a marketer and this were my business, this would be an absolutely thrilling result. We can see here that the regression line is really the best fit that minimizes what we call squared residual errors, and you're going to see this in the output from any kind of computer program. So I want to illustrate what this means. What regression line is actually on is the predicted value of all of the scores. That's what's forming the line. So the model is actually predicting every single value along its trajectory for every value that you could possibly imagine on the x-axis. And these are our actual observations in the sample. That's what's being marked on the graph. But the program has figured out that the sum squared error from the residuals, what we're calling the residuals, from the predicted line to the actual values are minimized by this line. So there's no other line that you could possibly draw on this chart that would minimize the distance between the observed scores in the gray dots and this line. This is the best one, and it's defined exactly by this equation. There's no better line that could be drawn. It's the most efficient one that minimizes those errors between the observed scores and the line itself. And this is what is so important. In this case, the actual sum squared error, as I'll show you in a moment, was 14. I'll show you how important that is in just a moment. Now, the other measure to keep in mind is what's called sum squared regression. The sum squared regression is the difference between that line that we just predicted, and if we knew nothing at all, we would just predict the mean value of the dependent measure, which is website visits, and that happened to have been 20. So if we knew nothing at all, we would just predict 20 for every single observation in the data set. And the sum of squared regression is calculating the difference between our prediction and what that would have been. And that becomes the difference on the regression line, called the sum of squares regression. In this case, it actually is calculated to be 100. And again, I'll show you how this works in just a moment. The final calculation that we need to appreciate that regression is doing for us is just looking at the mean of the web visits being predicted for everyone. The null hypothesis, of course, is that there is no relationship, and so this line should be really not significantly different than just predicting the mean for everyone. In this case, you can see that it is significant, but appreciate that the sum of squared total error would be the difference between this mean value being predicted for every single observation and the benefit that we get by predicting our regression line. You're going to see this all come together. So really, we're trying to improve upon this value, the mean, being just predicted for everyone. And that's what the regression line has done, as I've already shared. This is the best fit line that minimizes those distances, and hopefully it's done it at a statistically significant level, which usually would be a p-value of less than 0.05. In this case, we're far better than that. And so what we've just described is regression is basically just partitioning the sum of squared total error. This is the error that would occur in the sample if we continue to just predict the mean for the dependent variable for every single case. That's where the sum squared total comes from. The sum squared regression is the benefit that we get by actually calculating the line and minimizing the distance between the line and those actual scores. So we weren't perfect. We didn't explain all 114 sum squared error, but we explained a whole bunch, 100, and we only had 14 sum squared error remain. That's the error that's left unexplained. You'll see this formula written a number of different ways. Here's two different ways. I think I have a third coming up on another slide. But you can understand that this is just an algebraic relationship between these values, because all regression is doing is partitioning the sum squared total between these two amounts. There's also a relationship here to ANOVA. You might remember that we had sum squared error within and sum squared error between. There's really a very similar kind of conceptual relationship going on here, that the error between was sort of explained by the sum square regression, and the error within was left unexplained in the ANOVA table. And you're going to see how that thinking comes into play in just a moment. Now, one of the important benefits of this is we can calculate what's called a coefficient of determination in regression, which is just this ratio. This ratio of sum squared error in the regression that we were able to explain divided by the sum squared total. It gives us a ratio, and we can interpret that ratio as total sum square error accounted for, total variability accounted for. So when you see this R square at 0.8772, the interpretation would be that 87.72% of the variability in website visits, our dependent measure, can be explained by the linear relationship with web ads viewed. This is a marketer's dream. Talk about having some kind of ROI for the ads actually seen. Another way of interpreting it, web ads viewed account for 87% of the variance in website visits. So this will be an interpretation that we get to use in our regression models. Now, it's a funny thing, especially, well, really only with simple linear regression. If we only have one predictor in the model, if we take the square root of the r squared, it actually gives us the correlation coefficient. You remember a moment ago I said these techniques are related. So at least when you have simple linear regression and you only have one predictor in the model, you can actually take the square root of the r squared, and it would equal the actual correlation coefficient. In this case, it would be the correlation of web ads viewed to site visits. That would be 0.9366, which is a very strong positive correlation. Now, when you actually run this in SPSS, you will get output that's like this. You can see where you have some of the variables that I was just speaking to. Here's our r squared right here at 0.877. We'll be getting an F statistic, this value, and its significance, which we would typically set at p less than 0.05, is going to be telling us whether there's a significant relationship in the model for our predictors. In this case, we only have one predictor, one independent variable, which was web ads viewed. It's telling us here the dependent variable was the website visits. This is our predictor, ads viewed. Now, in the case where there's only one predictor, these two interpretations for the overall ANOVA model and the coefficient are going to be the same because there's only one predictor. But this will become more important when we get to multiple regression. You'll understand why there's another table. And here we have the actual coefficient for web ads that have been viewed, predicting our dependent measure of website visits. This is a t-test, and it's significant. And so here's some interpretations. We can take that. Again, web ads viewed account for 87% of the variance in website visits. The Pearson R correlation, which I would have received, had by taking either the square root of this or actually the model is giving it to us right here, is 0.94, a very strong positive Pearson correlation. The regression equation is written this way. Website visits, this is our intercept, B0. That's coming from here on the coefficient. That's called a constant. Plus 5, this is our coefficient for our predictor variable, web ads. And then we know that the independent variable was the viewing of those web ads. So that's how you'd actually write it. And the interpretation for every web ad viewed, website visits increase by 15. That'd just be putting in a value of 1 here, just for an interpretation that a manager might understand. Now, there are some assumptions with regression. First of all, normality. You probably get the sense that a lot of regression makes some kind of assumption about normality. Here, we're concerned about the normality of residuals that are independent and they're normally distributed. Luckily, there are some tests that we can look at in SPSS to help us understand that. Also, linearity. There should be a relationship between the independent predictor variables and the dependent variable, and the assumption for linear regression is that they're linear. And if you have a different assumption, there could be a different kind of regression that you may want to use. And also, there's this term of homoscedasticity. It just means that the variance of the residuals are equal for all points. And again, there are some plots and things that we can check. I also want to give you confidence that regression is generally very robust against these assumptions being violated. So if you see something that doesn't quite line up, I would definitely note it, but it doesn't necessarily mean that you have to stop the analysis. Unless it's really wickedly bizarre, I would still consider it and then just note where the violation was, and we'll look at how we can see some of that in the analyses. Also, it's important that for regression, at least for in our class, as we're looking at linear regression, unless I'm saying otherwise, the dependent measure for us is going to be a ratio or an interval. There are ways, and I will illustrate some dependent measures that can be dichotomous, and for that we're going to use logistic or other kinds of regressions to analyze that. Also, our independent measures, they need to be ratio or interval, but of course, again, you can use categorical or nominal, even ordinal variables as predictors. You have to be careful on the interpretation of what it means. And so mostly I'll be demonstrating ratio and interval in our class. And then there are, of course, ways to mix all of them and look for interactions similar to the way that we looked for those things in ANOVA, but they're just going to be beyond this session. Now, on the idea of residual plots, we'll be looking in the analyses for basically the standardized Z predicted value against the standardized Z residuals in these kind of plots. And generally what we're looking for is a pattern that's more or less a rectangle in these plots. I'll be demonstrating that to you, and that will indicate that we've not violated this assumption. If we see a pattern like this with very strong patterns where we have scores that sort of go in this funnel shape, and especially if they're plus or minus exceeding 3 standard deviations on the predicted, really it's either axis that you have to watch for this, that would mean that we have non-consistent variance and we may have violated that assumption. So we want to watch for that, but most of the time we can check for this pattern and see something that's more or less rectangular and feel safe that we've met that objective. Now in multiple regression we have more than one predictor variable on the factor, and this helps us actually have better predicted values on the dependent measure. That's why we want to add these. And it might look a little bit convoluted, but if you look at the pattern here, it more or less says, just like in simple linear regression, we still have an intercept. We have one predictor variable here. This is the actual predicted independent measure. And then we're just adding another independent predictor. And so the model just expands. All of these coefficients to get calculated at this point really do require matrix algebra. And so luckily, probably music to your ears, we're just going to let the computers do all of this for us. We're not going to be computing it by hand. I think you can definitely find some videos of people showing you how to calculate simple linear regression by hand. It's not too much different than calculating a coefficient, a correlation coefficient, Pearson coefficient by hand. But as soon as you get into multiple regression, it really gets to the point where your head hurts as you're watching it all come together. So we're not going to be doing that. We still keep the interpretation, though. All of these values represent basically an estimate of our predicted dependent measure. The thing to remember when you have multiple regression, we have to make the assumption that if we want to interpret this coefficient, it's done. Whatever value we have and we're interpreting here, it's done holding constant all the others. So all the others are kind of held constant and they're not varying as we're interpreting this. So that's one thing to remember in terms of interpreting the actual values when you have more than one. We're just assuming the other one is held constant, and then we can interpret the one that we want to focus our attention on. So those are different ways of representing multiple variables. When we have multiple regression, the R squared still is interpreted as a total amount of variance accounted for in the dependent measure. So all of what we've just learned stays the same with multiple regression. And so that's a good thing. We're still adding up independent variables to help us reduce the sum of squares error, and these relationships stay the same. As we are looking at the overall performance of the model, we'll introduce the concept of adjusted multiple coefficient of determination, because the only consequence of having multiple regressions is as we're adding in independent measures, it can actually reduce the sum squared error kind of artificially, and therefore make our model look stronger. So we can still interpret everything the same, but we'll be looking at, when we have multiple predictors, we'll be looking at a adjusted R squared, but the interpretation is the same. We have to be looking for multicollinearity. This basically means when we put in multiple predictors in the model, we want to make sure that the correlation among those predictors, our independent variables, is not super high. So it's just redundant if we do that. If we're pushing in two independent predictor variables that are both correlated at 0.7 or higher, we're not really adding any value in our model. And so it'd be better to leave one of them out. It could be the case that you need both of them in for some kind of theoretical reason or something you want to just test, but understand you're adding multicollinearity into the model, and it's not really appropriate to do that. You could be violating some assumptions or even making your model look like it's stronger than it really is. So we want to try to have the most efficient model, and we don't want to have a bunch of highly correlated independent measures if we can avoid that. Now, what about curvilinear relationships? I'm going to show you this scattergram, but this is the data. We can actually look at this in SPSS. If we're using a linear model to predict otherwise curvilinear data, so here's some example with a slight curve. You can see that it's sort of lower here, kind of goes up and kind of goes back down. We still might have a significant linear relationship, which we do in this, but we might be able to improve the model by having a curvilinear model. And so this is a special case where we do have that. In that case, it's not that difficult to actually do a curvilinear relationship. It's called a polynomial or quadratic model. It's a lot of words, but it basically just helps us fit a curved line, and it's just going to add a squared value into the model, which is going to help us make this prediction. But it's actually really helpful, and a lot of times business data does take this shape for seasonality or other reasons, and so understanding that it's not too much more difficult to look at the analysis with a polynomial or quadratic model. We'll just interpret the adjusted R squared. Everything else stays the same. Another special case is logistic regression or log linear regression. This is the case where we want to actually predict a dichotomous variable as a dependent measure. This can be super helpful when we have a model. In this example here, we're trying to predict whether or not a vehicle is an automobile like a car or a bigger vehicle like a truck based on horsepower and engine size. And when we do that, we're able to make interpretations in log linear regression or logistic regression such as this. As engine size increases, the odds that it is a truck increase by 10.75 times. Or you can get this interpretation as the engine size increases, it's 975% more likely to be a truck than a car, at least it is in this model. This is a huge difference. Similarly, as horsepower increases, the odds that it's a truck surprisingly decrease. So it actually shows here that there's a decrease. As horsepower increases, it's 3.9% less likely to be a truck than a car. We'll look at this example in a hands-on, but you can see how powerful this might be, and maybe replace automobiles and trucks with something like top customers and not top customers, or sale days versus non-sale day. It could be any kind of dichotomous value like that that you want to actually predict, and if it just has two levels, this might be a great opportunity to use this method. Another one that's similar to this that we touched on earlier in the class are counts. A lot of times we are looking at counts of things like maybe visits to a website, and you, of course, as any sample gets large enough, you could use general linear regression, but this is another opportunity to maybe do Poisson regression for counts if your data fit that, and we would be able to have a similar kind of an interpretation. So we're going to be looking at this example here. We have number of awards won in the year by students. That's just a count. Our predictor variables were math scores and a program that they were in, and we would be able to make interpretations in this case based on this model, such as compared to those in the vocational program, those in the general program were 31% less likely to earn awards, and those in the academic program were 104% more likely to earn awards. A 1 unit increase in math scores resulted in a 7% increase in likelihood to earn awards. And we'll look at how this model allows us to make all those interpretations. But I think you could agree that this kind of interpretation can be really powerful in business. It makes a lot of sense to business kinds of people. So it's important to understand these techniques and make them approachable. So the takeaway for today, we've looked at a use of linear regression to have a single scaled continuous variable predict a continuous dependent variable. We're contrasting this with ANOVA because ANOVA, we had levels or groups, and we were using those levels or groups, categorical data, to predict a continuous dependent measure. So this is regression is a great method when we have to evaluate two kind of scaled variables. This is really the preferred method. We can also use that with multiple predictors, and so it's a really flexible technique. And then we also looked at logistic regression and Poisson regression as ways of helping to understand the likelihood of events, and that's where we are actually using regression to predict just two levels. And at the 2-level area, it's very common to interpret it the way that I have in this session, and I think you can see it's very approachable. So it's sometimes beneficial to look at it that way than using a ANOVA.